Flipping into memories, space-time deep feature synthesis. We propose a model inversion approach for visualizing the learned internal representations associated with action classes by video models. We show that current model inversion methods cannot be directly extended to visualize representations of videos and address this by proposing an objective based on model priming that can provide more distinct representations of learned space-time concepts from multiple video models. Models for video understanding compositionally encode the space and time modalities of videos over large feature spaces. Proposed methods are based on different approaches for encoding the two modalities. However, there is little insight gain beyond metric evaluation. In cognitive science, stages of consciousness include the conscious, related to things that can be directly perceived, the unconscious, including thoughts, memories, or functions that are below conscious awareness, and the preconscious, including what can be recalled from memories and experiences. Recalling memories from the preconscious can be done through exposure to a certain stimulus, subsequently accessing relevant memory pathways. Our work is motivated by visually priming in cognitive science, whereby using an initial stimulus, models can be primed in order to access learned representations, providing a conceptual view of the model's spatiotemporal internal representation. Let's look at our methods in more detail. Given a video model for which we want to visualize learned concepts, we select a video instance of the class as stimulus and run inference, obtaining later representations across layers. We then define a trainable tensor with temporal spatial dimensions and run forward pass while also storing latent representations. We compute the class probabilities. We define a priming loss based on the Jaccard vector similarity between the C-length mean length vectors from the stimulus and the updatable input. To avoid direct correspondence to the priming stimulus and reduce a degree of freedom in the synthesized inputs, we include an additional verifier network. Given the synthesized inputs, we run inference and compare the mean and variance of the feature distribution statistics from the verified. This feature diversity term is used as a regularizer to the synthesized video. In addition, we include a second regularizer term to ensure continuity between synthesized frames, while also including diversity between frames further apart. This results in visualizations of concepts in which they include consistency in terms of the objects and can also represent motion. Looking at the regularizer in more detail, temporal coherence enforces similarity in representations of synthesized inputs for consecutive temporal locations, while increases the divergence in representations of further apart temporal locations. This term aims to both ensure continuity across frames, but also enforce the inclusion of motion. Feature diversity uses the batch norm distribution statistics of a verified network to regularize the mean and variance of the features from the synthesized videos. Given only a single stimulus, features from the synthesized video will primarily relate to those of the stimulus. This can be restrictive in the exploration of other, more general class features that are different from that of the stimulus or non-existent. By including the expected mean and variance of the verified network, these features can be better explored during optimization, providing more diverse visualizations. In our experiments, we expand prominent image-based methods to video and compare against them. We saw that naive extension of image-based methods is restrictive for video domain given low accuracies and inception scores of models on synthesized video. Qualitatively, for stimulus videos, optimization without deep dream or activation maximization results in noisy videos. Instead, videos from LEAPs are more visually distinct and can represent motions learned to be part of the action classes. We include further qualitative results on multiple architectures, and we update over all combinations of the priming objective. We also observe that learned presentations from our methods are within the feature distribution of real videos. Additional examples and explanations are available on our project website, and our code is also available online.